As we all know, Einstein, he created a theory of gravity which we call general theory of relativity, which is consistent with his older special theory of relativity. Newtonian gravity is not consistent with special theory of relativity because any change in Newtonian gravity is instantaneous, and therefore Einstein had to create a theory of gravity which is consistent with special theory of relativity, in which any gravitational changes must propagate with a finite speed, and therefore it is very natural that Einstein's relativistic theory of gravity, which is called general theory of relativity, predicted gravitational waves. Now, we all know that in Einstein's theory of gravity, the geometry of the space time is what is determined by the energy and momentum of the matter. So, typically the Einstein equation reads as follows. On the left hand side, you have the Ricci tensor r mu nu minus half metric tensor g mu nu multiplied by the Ricci scalar r, which is completely a geometrical attribute of the 3 plus 1 dimensional space time, and on the right hand side you have 8 pi g, where capital G is the Newtonian gravitational constant divided by speed of light to the power 4, which tells you that one is speaking of relativistic theory of gravitation, and 8 pi g by c4 is multiplied to the energy momentum tensor of the matter. I will shortly come to what is the physical interpretation for the energy momentum tensor, but one can show that from this Einstein equation you can write. So, therefore, Einstein could obtain as an approximation from this Einstein equation the familiar Newtonian equation for gravity. We know that in Newtonian gravity the equation is the Laplacian of the Newtonian potential is given by 4 pi g times rho, where rho is the mass density. One can show that the Newtonian gravitational equation, namely Laplacian of the Newtonian potential, is equal to 4 pi g by rho, follows from the Einstein equation in the weak field limit, where the G00, the 00 component of the metric tensor, is given by 1 plus 2 Newtonian potential divided by c square, and for static gravity the Newtonian gravity can be derived from the Einstein equations. Therefore, it was clear that Einstein's equation is more fundamental than Newtonian gravity, because under certain approximation, namely when the matter is not moving with speeds comparable to the speed of light, and when the matter, the gravity you are looking at is far from the matter distribution, so that you are looking at the weak field, then indeed Newtonian gravity can be obtained as an approximation from the fundamental Einstein equation. However, we want to study some new prediction of general relativity. Therefore, we would like to know this set of equations, which we think are the fundamental classical equation for relativistic gravity, namely Einstein's equation, does it predict anything new? For that, what we have to do is that we make weak field approximation, but we relax the time independence, that is, we can think of changing gravity. So, imagine that you have two massive objects rotating about the common center of mass, and suppose you want to understand what is happening to the gravity from Newtonian picture. In the Newtonian picture, if I am sitting here at point P and I ask what kind of gravitational field I will measure at point P in the Newtonian gravitational context, then because the two masses, let us say this is m2 and this is m1, because they are moving around the center of mass, the position of m1 and m2 is changing with time, and hence the gravitational field here that I measure is time dependent, because when m2 comes closer to this point P, the gravitational field will be stronger, more strongly attractive than when m2 is further away. But Newtonian gravity will say that this changing gravity is instantaneous. As soon as the mass comes here, the gravity here will instantaneously increase, while in Einstein's general relativity, gravitational perturbation, they cannot be instantaneous. The gravitational changes must satisfy the special theory of relativity, which means any causal changes that can only propagate with finite speed. So, changing gravity, therefore, we would like to quantify this new prediction of Einstein's general theory of relativity, namely when matter distribution changes in shape and size, how do the gravitational effects, which essentially are the geometrical ripples in the space-time fabric, how do they propagate? And that is where the prediction of gravitational waves come in. So, as a first study, what we will assume is that we have a matter distribution whose size is finite, and let us say we have our origin of the coordinate system to be inside the matter distribution. So, this is the matter distribution, and we are quite far. So, here is the observer, and let us say the vector that connects the origin to the observer, this vector is I represent it by r, while from the matter any point on the inside the matter distribution, call it P, this is the vector r prime, all right. And we want to know that when the matter is moving about, there is change in its matter distribution, size, etc., then what kind of changes would an observer which is very far away, so r is much larger than the size of the object. So, imagine that the size of the object is the maximum size is much small compared to r. So, under the condition that where one is observing the changes in gravitational field, this distance from the source is much larger than the size of the source itself. We want to know what kind of geometrical attributes do we have? First of all, it is given that the geometry is determined by the metric tensor g mu nu, and if there was no matter at all, that means the entire space time was flat space time, then we could have chosen a Minkowskian coordinate system where the metric would have been the Minkowski metric eta mu nu. So, if there was no matter at all, the space time was empty, then the trivial solution of the Einstein equation is the metric tensor once you have chosen the Minkowskian coordinate system. But the fact that there is some matter distribution tells us that your solution won't be Minkowski metric, rather now there is a non-trivial non-Euclidean geometry of the space time. But since the matter distribution is very far away from the observer, the correction to the Minkowski metric tensor, that correction will be small. So, therefore, I can add another term which represents the change in the geometry due to this matter which is far from the observer. So, I will add a term, and if the matter distribution is changing in size, shape, distance, then this changing metric perturbation will be a function of this r as well as time. But the fact remains that since I am very far from this size, the absolute value of the perturbation h mu nu is much small compared to the maximum values which reside in the eta mu nu. Eta mu nu, we know the time component is +1, 1 component is -1, 2 component is -1, 3 component is -1, and therefore, the fact that this metric perturbation is much small compared to the Minkowski background metric, our condition therefore is that absolute value of h mu nu is much small compared to 1. But since the matter distribution is changing with time, we also know that your h mu nu is going to change with time, and we want to understand how is this changing geometry related to the matter distribution. Now, because the absolute value of h mu nu is much small compared to unity, I can do a linearization of the Einstein equation. Let us go back to the Einstein equation. Einstein equation was given by r mu nu minus half g mu nu r is 8 pi g by c 4 t mu nu, where t mu nu represented the energy and momentum tensor of the matter. Because I am very far from the matter distribution, I expect that the metric fluctuation over the Minkowski metric to be extremely small. I can only retain linear orders in the h mu nu. So, I will only retain terms which are linear in h mu nu. So, therefore, let us rewrite what are the geometrical quantities in terms of h mu nu. First of all, we know that we have the crystal symbol gamma mu alpha beta, which is given in terms of the metric tensor themselves, where as usual the notation I have followed is when I write comma beta, what I mean is it is the ordinary partial derivative with respect to x beta. So, our notation is that any function f, when I say f comma beta, what I mean is this is del f by del x beta. Similarly, in our notation, the mu lambda upstairs is the contravariant metric, which by definition is g mu alpha, g alpha nu is the Kronecker delta mu nu. All right. So, the crystal symbol is given in terms of the derivatives of the metric tensor, but note that we are also having the contravariant metric tensor, and contravariant metric tensor is defined to be that which when contracted with the covariant metric tensor gives me the Kronecker delta. So, if G mu nu downstairs is eta mu nu plus h mu nu, then this implies that the upstairs G mu nu, namely the contravariant metric tensor, will be eta mu nu minus h mu nu, where what is this h mu nu upstairs? Where h mu nu is defined to be the raising and lowering is done by the Minkowski metric itself. So, therefore, eta mu alpha, eta nu beta, h alpha beta. The reason is that we are only including up to linear orders in the metric perturbation h mu nu. Therefore, although we would have raised it by using the proper metric, but that will only give you quadratic correction. So, therefore, we can immediately see that G mu nu, which is eta mu nu minus h mu nu, satisfies this result. Let us verify it. So, just to check that eta mu nu plus h mu nu contracted with upstairs, namely eta nu alpha minus h nu alpha, because I want to prove that these two indeed gives us the Kronecker delta. Remember, we have to only incorporate linear orders in h, because h is very, very tiny. So, let us expand the bracket, you will get but the last term is h mu nu alpha, which is quadratic in h. So, therefore, I will not be writing that is of the order h square. So, I will not take into account, and eta mu nu alpha contracted will give you the Kronecker delta. This is same as, because alpha nu are being summed over, and hence I can write it in this manner itself. So, that I will just I will raise this index. So, I will get h mu, nu has been raised to alpha, and here because nu has come down, again this is h mu alpha, and these two terms cancel. So, that I get delta alpha mu, which proves that indeed this object is indeed G nu alpha, given that this object is G mu nu. In other words, what we have demonstrated, that when we are writing down the crystal symbol, our G mu lambda, which is eta mu nu minus h mu nu, and these objects, since this the derivative eta mu nu is constant, the derivative will only be for h mu nu. So, this object will be simply h lambda alpha comma beta, this object will be h lambda beta comma alpha, and this object will be h alpha beta comma lambda. So, therefore, this object, if I include h mu nu, those h mu nu will only make quadratic correction. So, therefore, I just have to retain eta mu lambda, because the other term will only give you quadratic correction. So, in other words, what we have obtained is that gamma mu alpha beta, if I only take the linear orders in h, then I get this to be half eta mu lambda multiplied by h lambda alpha comma beta plus h lambda beta comma alpha minus h alpha beta comma lambda. So, you can see that because I am only talking about weak gravity and therefore only retaining up to linear orders in H, my expression for the crystal symbol is much simpler, and this is what I am going to use to write down the Riemann tensor, Ricci tensor, Ricci scalar, so that I have got linearized Einstein's gravity. So, let us now write down the Riemann tensor. The Riemann curvature tensor this is what embodies Riemann curvature tensor embodies the non-Euclidean geometrical aspect of the space time, and it is given in terms of the derivatives of the crystal symbol. Remember, comma means partial derivative with respect to the coordinate, and then antisymmetrize. Then again antisymmetrize. This is the Riemann curvature tensor, and if one wants to make a Newtonian counterpart of it, this tensor corresponds to the Newtonian tidal force field, and it is the tidal force field which is the actual gravitational field, not the gravitational acceleration, because when we go to a local inertial frame, the gravitational acceleration goes to 0, but the Riemann curvature tensor or the tidal force field is always there. Right. Now, look at the expression for the Riemann curvature tensor. Note that when we express the crystal symbol in terms of the metric perturbation H, we retained only linear orders in H, and therefore, when we look at the Riemann curvature tensor, there are quadratic terms in the crystal symbol, and therefore, when I include them, there will be only quadratic terms in the derivatives of the metric perturbation. So, they will be quadratic correction. I need not bother about them at all. So, in the linearization, when your metric tensor correction is very tiny, these two terms will not be important. They are quadratic correction, and hence I need to only take into account these two terms, which will be half eta mu lambda into h lambda, and then because this is nu alpha, nu comma alpha, but there is also a derivative with respect to beta, then there will be h lambda alpha comma nu, but again there is a derivative with respect to beta, and then minus h nu alpha with respect to derivative with respect to lambda, but there is also a derivative with respect to beta. So, there will be a beta. So, this is gamma mu nu alpha comma beta. Then there is also this term which is half eta mu lambda. Then again we will have h lambda nu comma beta, but there is a derivative with respect to alpha plus h lambda beta comma nu derivative with respect to alpha minus h nu beta lambda derivative with respect to alpha. The other two terms are corrections of the order of h square, quadratic correction. We need not bother about that. So, now I can take half nu lambda common, half eta mu lambda common, and get our all the expressions within a single it does not matter because h mu nu is symmetric. So, it does not matter whether I write lambda nu or nu lambda. This minus will become plus. Okay. So, we have put all the terms together, and therefore, now we will see some cancellation, and let us look at which are the terms that cancel. Now, look at this term, the nu alpha and lambda alpha, and look at the terms which are the quantities that cancel. Remember that comma beta alpha means there is a partial derivative with respect to x beta, partial derivative with respect to x alpha, but partial derivatives commute. H lambda nu is same as nu lambda. So, this quantity and this quantity will cancel, and we are just left with half eta mu lambda h lambda alpha comma nu beta. Then I will add the positive term first, plus h nu beta comma lambda alpha, then the two negative terms. So, let us verify whether all the terms have been taken into account. This is this term, this is this term, while the last but the remaining term is this term, and the last term corresponds to this term. Now, note the Riemann tensor of course is antisymmetric in alpha and beta, and we do have the antisymmetry here. As you can see, if you interchange beta and alpha, there is a negative sign here, there is a positive sign here. Similarly, there is antisymmetry in this. So, we have expressed the Riemann tensor, and of course, the order quadratic corrections we are not bothering about, we only want to retain the linear orders in H. Now, we want Ricci tensor, because in the Einstein equation it is the Ricci tensor and the Ricci scalar that appear. So, we have to express the Ricci tensor. So, R nu alpha by definition is you contract the upper index with the last index. In some books they contract the upper index with the second index, but that will be different from our only in a matter of sign. So, it does not really matter. I have taken the convention that the Ricci tensor is obtained by contracting the upper index with the last lower index. So, if I do that, the Ricci tensor becomes so wherever you have beta, beta will turn into mu. So, half eta mu lambda beta will become mu. So, let us see whether all the terms have come out to be correctly. So, here h lambda comma nu mu beta has become mu, h nu mu lambda alpha minus h nu alpha lambda mu minus h lambda mu nu alpha. So, this is my Ricci tensor, and hence the Ricci scalar which is by definition contracting G nu alpha with R nu alpha, which remember G nu alpha was eta nu alpha plus minus H nu alpha into R nu alpha, but H nu alpha term will only give quadratic correction. So, I need to only take eta nu alpha contract with R nu alpha. So, therefore, I will get this object to be half eta nu alpha into eta mu lambda. So, the other H nu alpha will only give me quadratic correction, I will not bother about it. Let us verify. So, half eta nu alpha, eta mu lambda, h lambda alpha comma nu mu, h nu mu comma lambda alpha minus h nu lambda mu minus h lambda mu minus h lambda nu alpha, correct. So, this is what is the scalar curvature R. So, we have expressed R nu alpha in terms of h, we have expressed Ricci scalar also in terms of h. We have omitted the quadratic correction because our h is indeed very, very tiny. Now, let us re-express, because I am raising and lowering only with Minkowski tensor. So, let us look at R nu alpha by raising the index using eta mu alpha. So, therefore, R nu alpha, I will use the eta mu lambda to raise the index. I have half h lambda will be raised to mu. So, you will have h mu alpha comma nu mu. Similarly, here plus here mu will be raised to lambda because mu is being, so mu will be raised to lambda. So, we will have h lambda nu comma lambda alpha. Here similarly, we will have eta mu lambda. So, let us write down. So, what is this object? I will have eta mu lambda, and here I have del square h nu alpha divided by definition this is del x mu del x lambda. Okay. So, this term I have taken into account minus eta mu lambda this object, eta mu lambda this object is trace. So, this is eta mu lambda, lambda is being summed over, mu is being summed over. So, that is the trace h comma nu alpha, okay, where the trace part so I will write somewhere or notation trace h is h alpha alpha, which is same as eta alpha beta h alpha beta. So, that is we are, since we are raising everything using Minkowski metric, trace of the metric perturbation, metric fluctuation is given by this. So, therefore, this object eta mu lambda minus h lambda mu, lambda mu is being summed over is given by this. Now, note what this object is. Minus eta mu lambda del square h nu alpha del x mu del x lambda. This is nothing but de-Elmbertian of h nu alpha, all right, because de-Elmbertian which is represented as this of any function is nothing but eta mu nu f comma mu nu, which is nothing but eta mu nu del 2f by del x mu del x nu. And because my eta mu nu is a diagonal object, eta 0 0 is plus 1, eta 1 1 is minus 1, and so on, this is nothing but 1 over c square del 2f by del t square minus Laplacian of f. All right. And hence, what we have shown is that this object is indeed the de-Elmbertian, and there is a h here which is also appearing. All right. So, let us look at the expression in somewhat more detail. So, probably what I will do is I will erase the top part so that we can directly manipulate. So, since eta mu lambda del 2 h nu alpha by del x mu del x lambda is the de-Elmbertian of h nu alpha, this whole thing can be now written as, so here this has become the de-Elmbertian minus de-Elmbertian of h nu alpha. Now, what I will do is I will split this minus h comma nu alpha into two halves. You will see why I am doing it. So, first I will have a minus half h comma nu alpha, and here similarly I will have again minus half h comma nu alpha. So, these two minuses add up to become minus h nu alpha, and then I will put this object here and put the other object there and see what happens. So, let me do that. Okay. So, I will first put this object here. So, h lambda nu comma lambda alpha. So, this I have already included, and this I will take it to the other side, plus note that this lambda is a dummy index, it can be made mu. So, just because a new symbol is appearing does not mean much, because I could have redefined lambda to be mu. So, let us verify all the terms have been taken into account. H lambda nu comma lambda alpha is here, and h mu alpha comma nu mu is here, and then I will close the bracket. You might ask, what have I achieved by this? The reason I am doing it is that I want to group two objects in a particular way, so that I can use the fact that in Einstein's general relativity I am free to use any coordinate system I wish, and thereby I wish to simplify my expressions, and that is the intention, and that is the reason I am doing a regrouping. So, this whole object can therefore be written as, first of all, there is a term, the de-Elmbertian term. So, let me write it as minus half de-Elmbertian of h nu alpha. That is one I have got. Then what I will do is there is a plus half, and this term, as you can see, is a derivative with respect to alpha happening common. So, there is a del by del x alpha happening here, and then I will have, so lambda, as I said, I can make it mu. So, mu nu comma mu, alpha derivative I have already taken into account. Similarly, here I have minus half h comma nu, because alpha derivative has been taken into account. Then there is this term. Again you can see that here there is a new derivative which is common. So, I can take plus half del by del x nu, then I have h mu alpha comma mu minus half h comma alpha. Okay. Now, you will be surprised to see that actually these objects can be written as a derivative of one unit. Let me write it first and then you will see why it is so. Let me first express and then you will see why it is so. So, what I will do is, although there is a derivative with respect to nu, let me write it as del derivative with respect to x mu, so that this becomes h mu nu. But then you will say, but here there was a derivative with respect to nu, not x mu, but I can use it. I can use the Kronecker delta. If I use Kronecker delta and I put, when mu is being summed over, if I put mu nu, then mu mu summed over will give del by del x nu. So, using the Kronecker delta, I can, when del by del x mu acts on it, mu mu summed over, only when mu is new it will pick up, because that is what Kronecker delta is all about, and therefore, I will get back this expression. Similarly, here I will take out the derivative with respect to mu del by del x mu, so that this is h mu alpha, but here the derivative was with respect to alpha, but here it is mu. So, again I will put a Kronecker delta mu, so that here I put alpha and I will get h. Okay. Now, note that these two objects are similar looking. Here the derivative with respect to mu contracted, here again derivative with respect to mu contracted. You will ask, what is the big simplification we can achieve by this exercise? I can demand a coordinate system where del by del x mu of h mu nu minus half del mu nu h is 0. Such a coordinate system is called harmonic coordinates, and therefore, what I am demanding basically is that I am demanding a coordinate system where the harmonic gauge condition is satisfied, which is del by del x mu of this quantity is 0, which is exactly the same. Once I use that condition, these two terms will go to 0 and my Ricci tensor will be simply minus half de-elongation of h nu alpha. So, that is the basic simplification I have got. So, go for harmonic gauge. Sometimes it is also called harmonic coordinate condition. Where you go to that coordinate system in which choose coordinates such that del by del x mu of h mu nu minus half delta mu nu h is 0. I will show why it is always possible in a short while. If I choose this coordinates, then clearly what happens is that my Ricci tensor r alpha beta simply becomes minus half de-elongation of h alpha beta. Okay. I will soon show you why this is always possible, namely harmonic gauge condition is always feasible, but what we have just now achieved is using the harmonic coordinate condition, my Ricci tensor is a very simple expression. And why is it important? Recollect that Einstein equation can also be written as R mu nu is 8 pi g by C4 T mu nu minus half G mu nu G alpha beta T alpha beta. That means G alpha beta T alpha beta is simply the trace of the energy momentum tensor. This equation is an alternate form of the original Einstein equation, this one. All you have to do is to get the other equation, multiply by the contravariant metric tensor G mu nu on both sides. You will soon be able to express R in terms of trace of T mu nu, substitute back, and then you will be able to get this equation. All right. Therefore, when you do not have any energy and momentum tensor, that means in those regions where there is no matter. So, in regions where there is no matter, in other words, what are those regions where there is no matter? The energy momentum tensor is 0. So, that is energy momentum tensor is 0. The Einstein equation is simply R mu nu is 0. So, in other words, the Einstein's theory tells you that in the region where there is no matter, the equation is simply Ricci tensor is equal to 0. Now, we go back, apply it in our case. So, where there is no matter, this, if I use this result, what I get is the D'Alembert of H alpha beta is 0. And what is this object? This object is telling me that the metric perturbation H alpha beta satisfies a wave equation where the wave speed is c. In other words, what we have derived from Einstein equation is, if metric perturbation is propagating, it propagates like a wave, because it box or D'Alembert of H alpha beta equal to 0 is a wave equation where the wave speed is c. That means gravitational waves move with speed c. This is we have, from first principle we have proved that gravitational perturbation move with speed c, and it follows from the Einstein equation. And hence, it is obvious that general relativity must be consistent with special theory of relativity, because any perturbation that does not move instantaneously, but it propagates with the light speed, namely 3 into 10 to the power 10 centimeters per second. So, if any matter, so if you go back to the original discussion, so if there is any material perturbation, what our equation tells us is this H mu nu, the metric perturbation, which is the ripples in geometry, this H alpha beta, these propagate with speed c. This is what we have proved from Einstein's equation. Now, we want to know that fine, if there is a metric perturbation, that will propagate with speed c, that is what we have derived. But how do we know what is the strength of the metric perturbation, how is it related to the matter itself? And therefore, we have to now, for that to understand, we have to go to the full-fledged Einstein equation, and I have to write r mu nu minus half g mu nu r in the linearized gravity in terms of t mu nu. Before that, let us also look at something we have derived, and it is this object that we are choosing a coordinate system where this object, its derivative with respect to x mu is 0. Now, note that this is equivalent to the result that del by del x mu of h mu nu minus half eta mu nu h is 0. Why? Because I am raising and lowering indices using the Minkowski metric tensor. So, here all I have done is raised the nu by multiplying eta nu sigma, that will raise it, and similarly the delta mu nu will become eta mu nu. So, therefore, this equation is also equivalent to this equation. This object h mu nu minus half eta mu nu h is called the traced reverse metric fluctuation. I will tell you why it is the trace reverse metric fluctuation. This is defined as h mu nu minus half eta mu nu h, so that the harmonic condition implies that the traced reverse metric fluctuation, if I differentiate with respect to x nu and sum it over, it is 0, which is same as del by del x nu of h mu nu minus half eta mu nu h. All right. Why is it called trace reverse metric perturbation? Because the trace of metric perturbation h mu nu happens to be negative of the trace of h mu nu. It is just by contracting with the eta mu nu will get it. So, let us do that. So, h bar, the trace by definition is eta mu nu h bar mu nu, which is eta mu nu h mu nu minus half eta mu nu h. Eta mu nu h mu nu is the trace of h mu nu, which is h minus half. Eta mu nu is nothing but delta mu mu, mu is running from 0 to 3, and therefore, it picks up a factor of 4, and hence h minus 2h is minus h. So, we have just now demonstrated that h bar is minus h, and that is the reason why we call it trace reverse metric fluctuation. Now, the harmonic gauge basically tells me that the trace reverse metric perturbation is such that h bar mu nu comma nu is 0. You might ask, how can we ensure that such a coordinate condition is always satisfied? So, to demonstrate that, let us use an infinitesimal coordinate transformation. Where our quasi-Minkowskian coordinate x mu is transformed to a new quasi-Minkowskian coordinates x prime mu, which is old x mu plus a small parameter epsilon times a vector field. The parameter epsilon is a small parameter. So, therefore, and xi mu of x comma t is a vector field. Therefore, under such an infinitesimal coordinate transformation, why is it infinitesimal? Because the parameter epsilon is very, very tiny. You can ask, what happens to the metric g mu nu? Remember, g mu nu is eta mu nu plus h mu nu. Under such a coordinate transformation, it will become g prime mu nu, which by definition, because it is a covariant tensor, so it will transform as del x alpha by del x mu into del x beta by del x prime, because this is a new coordinate prime, del x prime nu times old metric tensor g alpha beta. Okay. Because of this, I can write x mu also in terms of x prime mu, which implies that x mu is x prime mu minus epsilon zeta mu, and therefore, this object is simply del x prime alpha by del x prime mu minus epsilon del xi alpha by del x prime mu multiplied by del x prime beta by del x prime nu minus epsilon del xi beta by del x prime nu multiplied by g alpha beta. G alpha beta is eta alpha beta plus h alpha beta. Now, note that because x prime alpha is also a valid coordinate system, so del x prime alpha by del x prime mu will be Kronecker delta alpha beta. Why? Because each of these coordinates, they are functionally independent of each other, and so we know that del x prime alpha by del x prime del x prime alpha by del x prime beta must be the Kronecker delta alpha beta, because only when alpha and beta are identical, then del x prime alpha by del x prime alpha will be 1, but alpha beta are not identical. These are functionally independent coordinates, therefore, their partial derivative must be 0. Because of this, this result simply becomes delta alpha mu minus epsilon del x prime mu, because there is a derivative with respect to x prime, I can always write it as del x beta by del x prime mu del xi, okay, let me choose beta 1 del xi del x beta 1 multiplied by del x prime beta by del x prime nu, which is of course delta beta nu, but let us also write what this is. Del, similarly, I can put del x beta 2 by del x prime nu into del xi beta by del x beta 2 multiplied by eta alpha beta h alpha beta. But because del x beta 2 by del x prime nu, again it will have Kronecker delta plus minus epsilon times this, but that epsilon will only give a quadratic correction epsilon square, but epsilon is very, very tiny. We want to keep only up to linear orders, and hence this object is just Kronecker delta, and we will get del xi beta by del x nu itself. So, in other words, this becomes simply del alpha mu minus epsilon del xi by del x mu itself, because this will give me a Kronecker delta beta 1 mu, and when you contract it, you will get del x mu itself, and here similarly delta beta nu minus epsilon, similarly Kronecker delta contracted del xi beta by del x nu multiplied by eta alpha beta plus h alpha beta. The other corrections are quadratic in epsilon. We do not want to take quadratic correction, we only retain up to linear order is epsilon, because epsilon is very, very tiny. When I open up the bracket, remember I will only take the epsilon linear orders, all right, and therefore, I will the final term epsilon square I will discard, I need to only take linear orders. So, we have got this expression, we want to simplify. So, therefore, since we have got this result here, I will erase the top part and do the simplification here. So, what we saw is that under infinitesimal coordinate transformation, the old metric g mu nu, which is eta mu nu plus metric fluctuation h mu nu, goes to new metric g prime mu nu, which is given by this expression. So, now let us simplify this expression and go to this object, and what we find is that g mu nu, which is eta mu nu plus h mu nu, has now gone to g prime mu nu, which is this is minus So, let us term by term make the simplification, noting that epsilon is very tiny, h alpha beta is tiny, and we are only keeping things up to linear orders in epsilon and linear orders in h alpha beta. So, therefore, this object becomes when I take this in, I will get eta alpha nu plus h alpha nu, and then this I have taken. When I hit this, epsilon and h alpha beta will be quadratic in smallness, hence I will only take this into account. So, I will get minus epsilon eta alpha beta del xi beta by del x nu. Then again I will open up the bracket, so that I get delta alpha mu alpha into eta alpha nu plus h alpha nu, which will act on this. The smallness, since I want linear orders, smallness will hit this. So, there will be a minus epsilon eta alpha nu del xi alpha by del x mu, and this term with this will be quadratic. Similarly, we know that this term with this term will be quadratic, and only this term with this term will be left, which is only linear in epsilon. So, I will get epsilon and delta alpha mu eta alpha beta del xi beta by del x nu, so that all others are small, and hence when I simplify I will get this object becomes eta mu nu plus this object becomes h mu nu, and finally this object becomes minus epsilon. Alpha gets lowered to nu, so I get del xi nu by del x mu, plus here you can see that this becomes eta alpha beta, xi beta becomes xi alpha lower, but xi alpha lower with alpha Kronecker delta contracted becomes del xi mu by del x nu. So, in other words, what we have demonstrated, this is eta mu nu plus h mu nu minus epsilon xi mu comma nu plus xi nu comma mu, where I have written first this term here and then this term here,